Hey, hello, everybody. Doug Beavis here to introduce a good friend and colleague, Dr. Aldo Bernasconi. He's going to present a presentation about the effects of omega-3 dosage on cardiovascular outcomes today. Aldo is the Vice President of Data Science for the Global Organization of EPA and DHA, or GOED. His experience as a data scientist includes modeling, algorithm development, and data analysis in a variety of fields, including biostatistics, bioinformatics, and market analysis. His responsibilities include coordinating the collection, analysis, and dissemination of information relevant to omega-3 markets, the development of GOED's clinical study database, and scientific research on the role of omega-3 fatty acids in health. Aldo holds a PhD in mathematics from the University of Utah. So it's my distinct pleasure to introduce my friend and colleague, Dr. Aldo Bernasconi. Aldo.
Thank you, Doug. Good day to everybody, and thank you for being here. So what I'm going to be talking about today is a little bit about the effect of omega-3 dosage on cardiovascular outcomes. Mostly, I'm going to be presenting results from a meta-analysis for which I'm the first author. This was published by the Mayo Clinic Proceedings a few months ago online and 2 or 3 months ago in press. So let me start by introducing GOED in a little more detail. So GOED is a trade association dedicated to EPA and DHA. Our goal is to promote the consumption of EPA and DHA globally, which what we're trying to do is to get people to use a sufficient amount of EPA and DHA for the benefits that you can obtain from it. We have 170 member companies through the entire omega-3 supply chain. This is globally, and our members have to adhere to very strict quality standards that we have established. So our work includes regulatory, scientific, communications, market research, and technical issues. So that is the quickest introduction I can give you. I included this slide not only to introduce GOED, but to remind you of the fact that I do work for the omega-3 industry. So this is a bit of a disclaimer too. You have to consider carefully the arguments that I'm going to make, because there's at least a perceived conflict of interest. Because of that, I'm going to leave in every single slide in the bottom right, there's going to be GOED's logo, just to remind you of the fact that there's this, so you need to examine my arguments carefully because of that. So let me give you a little bit of the background in here. EPA and DHA are among the most studied compounds in the scientific literature. If you go to PubMed and start mining articles, taking a look at which ones are the ones for which there are more studies published, EPA and DHA are up there with penicillin and folic acid and vitamin E. They're in the top 10 most studied compounds. And we're talking about in here about in PubMed alone, 40,000 articles about EPA and DHA, of which between 3,000 and 4,000 are interventional trials. There's a lot of research on EPA and DHA. It started a long time ago. The oldest article indexed by PubMed about EPA and DHA, or what appears to be EPA and DHA in some way, is an article from 1782. It's an article about cod liver oil that concludes that cod liver oil actually helps with rheumatism. So it's this is not something surprising for us in this field. There's a long history of research on EPA and DHA and its effect on arthritis and such diseases. The study concludes that there's a beneficial effect on people who were otherwise unable to walk. By taking cod liver oil, they recover the mobility and reduce the pain. The research continues, of course. This is a number of articles published every single year that are indexed by PubMed, and what we're seeing is roughly 250 new articles every single month. So very active field of research to this day. Quite a bit of this research has been conducted on cardiovascular outcomes. This is why people take fish oils or eat fish for the cardiovascular benefits. We know of 1,100 articles on cardiovascular diseases. These are just interventional articles in humans. And then hundreds more articles in subjects that have something to do with the development and the progression of cardiovascular diseases, things like diabetes, hyperlipidemia, and inflammation. So as you see, a lot of research in here. Because of all of this research, several countries and several organizations have issued intake recommendations. And I cannot, it's not the point of this presentation to walk you through every single recommendation out there, but I'm just going to say quickly that governments and scientific bodies typically recommend some amount between 250 and 500 milligrams of EPA and DHA per day for overall health, and then sometimes slightly higher quantities for specific life stages or health conditions. So there's recommendations for people with a history of cardiovascular disease, there's recommendation for pregnant women, things like that. A typical recommendation is GOED recommendation, which is 500 milligrams for general health, and a little more, mostly DHA for pregnant women, and a gram for people with established cardiovascular disease. ISFO recommends 500 milligrams per day. All of this is roughly typical. So as you see, I mean, there's a belief in the benefits of EPA and DHA. There's a lot of research behind it, and there's recommendations based on this. So what is the problem in all of this? Well, to start with, there's a very strong, there's strong evidence for the fact that EPA and DHA reduce cardiovascular risk. And it comes from several different sources. I mean, let me start a little bit with the epidemiological evidence. So we all know for a long time, you know, that eating fish is good for you, but there's also more detailed investigations on epidemiological research in a little more details on that. And possibly the most complete body of evidence on this regard is the work by Bill Harris, who developed the Omega-3 index, which is a way of measuring the amount of EPA and DHA circulating in blood, specifically in phospholipids in red blood cells. So Bill put together a group of researchers who collected the results of 16 different studies, 40,000 individuals in these studies covering 10 countries, mostly, I mean, balance between men and women, middle-aged, and these people were followed up in this study for a median of 14 years, and 14,000 people died during this studies. So what Bill did is he took a look at what were the levels of EPA and DHA at baseline in the studies, and whether this would predict mortality during the study. And in fact, it does. If you take a look at this, what we are seeing is what they did is they just simply divided people according to the levels of EPA and DHA in quintiles, and they compare the first quintile with the second, the third, the fourth, and the fifth. The highlighted graphing here shows you the risk for cardiovascular disease mortality, and as you see, there's a very nice linear trend going down. The higher the levels of omega-3 in blood, the lower the risk of cardiovascular disease mortality. This is fairly typical work of the very typical representative of the kind of work that Bill has been conducting now for decades. This is possibly the most detailed analysis with the most data behind it, and it's been consistent. You know, the more omega-3 in your body, the more protected you are against mortality, particularly cardiovascular disease mortality, which is the topic I'm covering today. Eventually, this was, by the way, by a presentation that Bill gave last year. Eventually, the contents of that presentation made it into a publication that came out maybe a month ago. By that time, there was a 17th study in there, so now we're talking about 42,000 people being studied in here. And it found exactly the same result. I mean, higher levels of omega-3, bigger cardiovascular protection. There's always, of course, some critique of epidemiological evidence, which goes roughly like this. Sure, people who eat more fish are protected against cardiovascular disease. But eating fish, because we all know that fish is good for you, is a healthy behavior. And people who observe one healthy behavior are more likely to observe other behaviors like that. So, you know, people who eat fish are more likely to exercise, to keep a healthy weight, to take the vitamins, to go to the doctor, things like that, because they are concerned about their health. So there's many, many healthy behaviors together. That is a very valid argument. What is new in this study that was recently published is that using standard statistical techniques, the effect of omega-3 content in blood on cardiovascular mortality was studied controlling by all of the socioeconomic and lifestyle variables you can think of. So by BMI, the control by education, by physical activity, by alcohol intake, diabetes, general health, and so on. So even after you control for all of that, the effect is very strong. Strong enough so you can see the relationship in here in this plot between EPA and DHA and cardiovascular mortality. The bottom right shows you the plot for EPA plus DHA, and as you can see that if you go from the 10th percentile, which is roughly an omega-3 index of 3.5% or so, to the 90th percentile, which is an omega-3 index of a little close to 8%, I think slightly below that, then you can see how the risk reduces by a good 15%. So I think that this is a fairly strong, the strongest epidemiological evidence that I have seen about the fact that EPA and DHA do reduce the cardiovascular mortality. These are the results from the same study, telling you how each one of the fatty acids, the components of the omega-3 components, are related to cardiovascular mortality. Very strong effect, at least for the long chain fatty acids. The second piece of evidence telling me that there's strong evidence for cardioprotective role comes from animal studies and from cell line studies. There's, as far as I know, about 15,000 animal studies involving EPA and DHA and 10,000 studies conducted in cell lines. A big body of evidence. And this body of evidence finds that there's several mechanisms that contribute to cardioprotection. So this is complicated. There's reduction in the triglyceride production, there's reduction in blood pressure, there's reduction in thrombosis. What I'd like you to take out of this slide is that there's very carefully studied basic science studies telling you that there's several mechanisms explaining a cardioprotection. And I prefer when I see a claimed effect, I prefer to see some biological justification. I prefer to see, hey, fine, can you explain why this is happening? So I can have at least some biological plausibility in my head about that. And there is several mechanisms indeed that would explain a cardiovascular protection, that effects and processes that are modulated by omega-3. What is very interesting in here is that different biological mechanisms depend on dosage in different ways. I think that it adds to plausibility when you see a dose effect relationship, because, you know, I mean, several things should work in that way. The higher the dosage to within certain limits, the higher the effect. There is some of that in here. And this is, by the way, a slide that is 10 years old from a study by Mosaferin and Wu. This was before all of the explosion in research on lipid-mediated resolution of inflammation and things like that. So even though it is an old slide, it still makes a very good point of the multitude of effects going on in here. The third piece of evidence that makes me claim that there's strong evidence for the cardioprotective effect comes from interventional trials. And this is where my work starts. So if you take a look at, say, coronary heart disease events, there's 35 or so trials that have lasted more than a year that have studied this. And if you meta-analyze these trials, then you can see that the effect is a protection of about 10%. Taking omega-3s, these are interventional trials, taking omega-3 results in a 10% risk reduction. It is statistically significant. This is a positive effect. 10% is a very nice magnitude of an effect for something that has essentially no serious side effects. But there's certain things in here that make life a little interesting. The first thing is that the results are heterogeneous. I mean, if you take a look at the statistics in there, you can see, I mean, there's some heterogeneity in the results, which is a little bit surprising. And the second thing is that if you look at the results of each one of the individual trials, they're all over the place. Some of them are positive, some of them are slightly negative, most of them are close to no effect. So as a result, I mean, the results are extremely variable. If you take all of the results together, if you put this body of evidence together, then you find a strong argument for the fact that there is indeed a benefit. But if you look at the individual studies, they're all over the place. And this is a problem. The results of interventional trials are highly variable. Some are positive, some are neutral. I haven't seen any that is negative, but this makes interpretation challenging, and it makes the explanation very challenging. So you have sometimes, you know, one study comes up positive, and there's a lot of press coverage claiming that omega-3s are indeed protective. Then the next study is going to come back neutral, and then you're going to get all kinds of both academic and popular press discussions saying, oh, there's nothing in here. And every single study we go through that. Again, that is a problem that I need to talk about today. So how do we address this heterogeneity? Well, we start studying what the causes of the heterogeneity are. We start taking a look at what are the variables that may explain the differences. So what we did is we conducted a systematic investigation of the reasons for this. And using the existing data that has been published in trials, we used a meta-analysis to do that. And we focused on a few possible explanations for why the trials are all over the place. The first one is differences in dosage. Does dosage make a difference? The second one is, does baseline risk make a difference? Does the year of publication, do newer studies tend to be more or less effective than previous studies? And does composition make a difference? Is EPA more effective than DHA or vice versa? It's a topic of very, very active research right now, and one for which we don't have an answer. So there were some other obvious explanations that we would love to be able to explore for which there's no sufficient evidence. So it would be very good, for example, to have some data on baseline status or baseline intake of omega-3 of the participants of a trial, but that, except for very few trials, mostly recent ones, the data just doesn't exist. So the results came out, as I mentioned, in the Mayo Clinic proceedings a few months ago, and that is the title. I'm the first author in here. The other authors, Michelle Wist is a biostatistician who, because I needed somebody to verify that I'm doing things right. I'm not a statistician. I'm good with numbers, but I'm not a statistician. I need somebody to verify my assumptions and calculations, and then the rest of the authors, Carl Levy, Rachel Milani, and Jerry Laukanen, they're cardiologists who provided the interpretation and provided the commentary and made sure that we were talking about reasonable stuff and the conclusion was reasonable. The data that we used came from a Cochrane meta-analysis conducted by Abdelhamid and all, and other people. This was published originally in 2018 and updated in 2020. And all of the trials included in there were 12 months or longer. We thought about the possibility of extracting the data ourselves, but because meta-analyses are dependent on the assumptions that you use in extracting the data, we saw that it was wiser because of a perceived conflict of interest in my part to rely on data collected by somebody else. We did have a difference though in our study design. While the study by Abdelhamid includes trials in which the intervention was giving people EPA plus DHA or giving them advice about eating more fish, we decided only to focus on studies that had an actual EPA plus DHA intervention. We omitted the trials that gave advice. This was for two reasons. The first one was because it's very difficult to know what the dosage is in a trial in which the intervention is advised. The second is because it's a little unclear what the question is if you include advice. Let me be a little more specific. If you give people EPA and DHA, then the question that you're answering is, do EPA and DHA have an effect? If you give people advice, then the question that you're answering is, does giving people advice to eat more fish make a difference? If you combine the two, then the question that you are answering becomes less clear to me, and that is the reason why we omitted advice trials. We focused on a few outcomes: cardiovascular disease, because most trials on the subject use that as a primary outcome; coronary heart disease events and myocardial infarction, because it is fairly understood that most of the effects that you see from omega-3 supplementation are cardiac in nature; and CHD, so coronary heart disease mortality and fatal myocardial infarction, because cardiac mortality is the reason behind most of the recommendations out there. And we conducted a meta-analysis. This is fairly standard. It's a random effects meta-analysis, and then we conducted a meta-regression using as predictors all of the variables that I have described so far. And the results from the meta-analysis, I mean, this is just putting together all of the variables, is we found a significant protective effect against myocardial infarction, coronary heart disease events, fatal myocardial infarction, and coronary heart disease mortality. For overall cardiovascular disease events, the effect was not statistically significant. It was close, but it was not statistically significant. These are the results. This, if you take a quick look at the last couple of columns in here, the heterogeneity is either low, moderate, and well, you know, I mean, moderate is a concern. I mean, there's reasons to investigate why there's differences in the trials. And the final column, the final plot asymmetry, is the only way that that is commonly used when conducting meta-analysis to assess whether there's a little bit of a publication bias. And we didn't find any evidence of publication bias except for CHD mortality. And that is indeed a concern. It makes the results less reliable for that outcome. We evaluated the strength of the evidence using the GRADE framework, and we found that for CVD events, MI and CHD events, the strength of the evidence was high. And for fatal MI, it was moderate, and for CHD mortality, it was low. What this means, actually, what high strength of evidence means, colloquially, is, you know, somebody else is going to publish a new study. What we are saying when we say that the evidence has high strength is that chances are that is not going to change our estimates by all that much. If it is moderate, then that means that it's likely that it's going to change the numbers, but it's not quite likely that it's going to change the conclusions. And if the evidence is low, it's just, you know, I mean, this is our best guess. New evidence may really change both the magnitude and the conclusions. All of these numbers, we of course built a linear model to evaluate the effect of dosage in these results, and we found that it was significant for CVD events and for myocardial infarction. And translating this into easier numbers, an additional gram per day reduces the risk of CVD events by about 5.8%, an additional gram a day reduces the risk of myocardial infarction by about 9%. This is a plot of what the effect of dosage is in CVD events. One of the ones for which this was significant. As you can see, I mean, each one of those blobs is a trial. Larger trials get larger blobs, and you can see how that as dosage goes up, the relative risk goes down, which is what we want to see. And we see that this line goes to the origin, which is a sanity check. You know, no dosage. We shouldn't see an event. This is consistent, very strongly consistent with the idea that dosage matters. Same plot for, and same observation for myocardial infarction. The effect actually extends to the entire range of the dosages between 0 and 4 grams. And these are the protections that, according to models, we should be seeing for myocardial infarction and CVD events. And this is fairly consistent with the data from the 40 trials that were included in our analysis. Now we get to year of publication. There's a common belief among researchers that earlier trials were successful, but that as time went by, the trials became less and less successful. This quote in here, I have to confess, I'm slightly ashamed about that. I wrote that one. It's a quote published years and years ago, resulting from a talk that I participated in. It was a workshop at an East Fall meeting. And in which I was making the point that, you know, earlier trials were more successful than newer trials find a smaller effect. And the belief that this is so has been floating around for a long time. And there's different explanations about why the year of publication may affect the results or may affect the effectiveness of EPA and DHA. One possible explanation is that it may have something to do with, you know, the 30 or 40 years that we have been studying this, clinical trials have improved. We have better techniques to do that. Or maybe there's some kind of an interaction with current cardiovascular prevention, treatment, or detection. I mean, everybody's in statins now. 40 years ago, that wasn't it. Maybe there's some kind of an interaction. This is a valid point. Maybe trials have become less effective over time. It turns out that if you analyze the data and you build a regression using the year of publication as a predictor, whether you include dosage, because the effect of dosage is so big, whether you include it or not, there's no evidence whatsoever that the year of publication has any effect. So this belief that trials have become less successful over time is not supported by the totality of the evidence. That surprised me, actually. I expected to see an effect. The second thing is that that's a good question. Do omega-3s, are omega-3s more effective in people at a higher risk or people at a lower risk? So what we did is we modeled the results, the relative risk, based on baseline risk. Well, not really baseline risk, but the risk in the placebo group, which is the best proxy we have for what the baseline risk was in each one of the population studied. And we found that dosages being equal, EPA and DHA supplementation is just equally effective. Whether you're talking the relative risk that you see, it's just the same, independently on whether you are at a high risk or at a lower risk. So it appears, and there's more research that needs to be done in here, it appears that EPA and DHA for equal dosages was just as effective if you do primary or secondary prevention. The last question we're testing here is one of composition. It's a question that has been studied a lot in the last 2 or 3 years. And the question is EPA more effective than DHA or vice versa, or it doesn't matter? This was prompted actually because of the publication of the REDUCE-IT trial. REDUCE-IT is a trial that was widely successful. It found 25% risk reduction in multiple cardiovascular outcomes by giving people high doses of EPA and EPA alone. So it renews the discussion about whether EPA is more effective than DHA. The problem is that reducing not only gave pure EPA to people, but it gave them a lot of that, almost 4 grams a day. And remember, the recommendations are 400 milligrams. Typical intake in the United States is 160 milligrams. I mean, 4 grams a day, that's an enormous amount. So it's impossible, I mean, it's just by looking at reduce it by itself, it's impossible to know whether the effect was due to the fact that it only uses EPA, or whether it was due to the fact that the dosage was so much larger than anything else. So it prompts the question, is EPA more effective than EPA plus DHA? So the way you assess this question, or the way we number of people assess this question, is by building a linear model. What does it really mean when you say that one treatment is better than another? If you plot the effect of the two treatments due to dosage, it can mean two possible things. Either that the line for one of the treatments is higher than the other, which would indicate, one possible definition of this is better. The other one is if the slopes are different. If the slopes are different, one of them, as you increase the dosage, is going to become more effective than the other. So those are the two questions that you can, the two possible meanings to that question. And the way you model that is by building a linear model that uses a variable that asks, is this pure EPA or not? An interaction term, is it only EPA, is going to tell you whether there's a difference in the height of the lines, and the interaction term is going to give you an answer to whether there's differences in the slope. And we control for the dosage because dosage is so influential that it can obscure the finding for other variables otherwise. But whether you include the dosage or not, there's no significant, we did not find any significant compositional effect. We could not find EPA to be more effective than EPA plus DHA, or vice versa. The evidence existing to this day does not, if you take the evidence in its totality, not just focusing one trial at a time, but the evidence in totality does not tell a story that says that one of these fatty acids is better than the other. It's entirely possible that that is the case, but the evidence is not sufficient. Additionally, we conducted some sensitivity analysis. We asked the question, what happens if we remove reduces from this analysis? And the thing is that removing reduces from an analysis does not change any of our conclusions. So the conclusions of our study are not depending on reduce it. And because of these two factors, both the fact that we could not find a difference in the linear models and the fact that we did not find a difference when we eliminated reduces from the computations, we had to conclude that there's no evidence. We cannot conclude that EPA alone is more effective agent for CVD prevention than EPA plus DHA, at least for the outcomes that we covered in this review, not from the currently available evidence. So the conclusions of a meta-analysis was that, yeah, indeed, EPA and DHA supplementation is an effective strategy for reducing the risk of at least certain cardiovascular disease outcomes. This was written, by the way, by the cardiologist, not by me. I have to. I do believe that the role of a statistician, or the role of the data analysis, look at the data and leave interpretation to the people who are specialists in the field. And the conclusion is that it is cardiopreventive, and given that the risks are minimal and there's no known interactions with the drugs used for cardiovascular prevention, then it is a good idea to use this, and possibly at higher dosages than what is in the recommendations. And possibly there's a role in supplementation because it is difficult to obtain these levels just by eating fish alone. And those were the conclusions of the study, and we were very happy for a few weeks. But of course, the only thing that is constant in life is change, and somebody published a new trial. A couple of new trials, actually, which has completely appended all of this. Two trials. Published just in November 2020. The first one is OMEMI, and the second one is Strength, both of them very well-expected trials, and people that have received a lot of attention. And both of these trials, which use fairly decent dosages, were neutral. They found absolutely no effect whatsoever in cardiovascular protection, at least for the prevention of cardiovascular disease events, which was the primary outcome. We updated a meta-analysis and included these two trials. This was published in a letter to the editor of the Mayo Clinic Proceedings. That letter made it to press just this week. And we did not find any change in the list of positive outcomes of the meta-analysis, and the changes in the numbers in the estimates of what the effect were very slight. This is the updated slide showing all of the effect, and personally, I cannot see the difference between this slide and the previous slide where I showed you the original results of the meta-analysis. I can only tell the difference by taking a look at the numbers of studies and the number of participants in the left. The effect is still dose dependent for myocardial infarction, but if you remember, it used to be dependent for CVD events, not anymore. That was the only thing that changed by including these studies. So there's still no differences by either publication, there's no differences by baseline risk, and there's no differences by whether the study included EPA only or EPA plus DHA. So let me talk a little bit about each one of these studies. OMEMI was a study in which people were given a little more than 1.5 grams per day for 2 years, and they found absolutely no effect whatsoever. The thing about OMEMI is that it's an underpowered study. If you're talking about effects of this magnitude, I mean, if you use my linear model for dosage, then 1.5 grams, 1.6 grams, should be associated with a 9% risk reduction. And with that risk reduction, then a trial with 1,000 participants using the common assumptions and the risk that was found in there and so on, it only has an 11% power, statistical power. It only has an 11% chance. If you assume that the effect is real and that dosage should provide a 9% risk reduction, then this trial only had about a 10% chance of detecting that, which is not sufficient. But the second thing about OMEMI that made it very, very unusual is that it was conducted in Norwegians. This is a plot showing you the omega-3 index, the levels of omega-3 in blood of people in different places. Now, there's a decent amount of research saying that the optimal range for the omega-3 index is somewhere in the 8 to 12% range. And 8 to 12% range is something that is only achieved in very, very small places in the world and places that consume a lot of fish. Alaska, parts of coastal China, Japan, and yes, Norway. So the thing is, Norwegians are already in the optimal range, and it is not clear that giving additional EPA and DHA is going to do much good. There has to be a moment at which additional supplementation just doesn't do any good anymore. So this makes this study a very unusual one. It was conducted in possibly the only population or one of the few populations in the planet for which you didn't expect much of an effect because they were already in the optimal range. Strength, on the other hand, that was a surprise. So this is a large study, has 13,000 participants. People were giving 2.2 grams per day. The risk of major CVD events was exactly the same in the placebo and the treated group. That came as a surprise. They were big enough. An observation by Calder and Deckelba is that if you just take a look at the EPA that was given to these people, if you believe that EPA is what is effective in here, which again, there's not much evidence for, but if you believe this study is giving people more EPA than jellies did. Jellies was a study in the Japanese population a few years back, and it found a significant effect. So just EPA alone should have been enough for an effect. So something is unusual in here. It is surprising. This result is surprising. And it was, of course, I'm going to skip this quickly, but the statistical power more than sufficient. The thing is that the results of reduce it and strength are very different. The two top lines in there show you how events occurred in people as time went by in reduce it, and you see a big difference between those two lines. In strength, the two lines are overlapping each other, and then at the bottom you have jellies for which you you see a small separation between the lines, but that separation is enough to conclude that there's a statistically significant benefit. But in strength, no such a thing. So people have focused a lot lately on reduce it and strength. There is clearly difference. You can even see that the treated group in reduce it was at a higher risk, the line is higher, than both groups in reduce it. So there's differences between the two trials. And there's controversy about the reasons for this difference. Sadly, the discussion has been focused only on these two trials, and this is a bad idea. There's been two arguments that are floating around. There's a lot of discussion around these arguments. The first argument is that reduce it got it wrong. Strength is the right one, and reduce it only saw an effect because they used mineral oil as a placebo, and mineral oil is bad for you. I'll go in more detail into this explanation and why I don't find it to be particularly convincing. But that is one of the arguments. No, strength got it wrong. Reduce it is right. Reduce it got it wrong. They just used the wrong placebo. Strength is the one that found the right effect in here. And the other side is, of course, the side that says that reduce it got it right. Strength is wrong, and that is because EPA alone is good for you. Those are the two arguments. Both of them are unconvincing. I actually find it regrettable that the discussion has been circumscribed to only these two trials. Because strength and reduce is different in many ways. They use different placebos, they were conducted in different populations, the risk profiles were different. I mean, even the treated group in reduce it was at a higher risk than strength. Dosage was different, composition was different. One of them had only EPA and DHA, only EPA, the other one had EPA and DHA. The chemical form was different. One was an ethyl ester, the other one was a carboxylic acid, which had never been studied before. So there's many, many differences. And these are the only differences that I can get out of writing a slide in a few minutes. So looking at these two trials, it is impossible to determine which one of all of these differences is the one that explains the differences in the behavior of the trials. I wish we knew more. I wish we had a better explanation. But just looking at these two trials or picking a couple of trials or additionally, to strengthen your point is not going to do it. So let me go to each one of these things in detail. One of them is the bad placebo hypothesis, which is basically says that the mineral oil, which is a placebo used in reduce it, interferes with the absorption of statins and increases cardiovascular risk, or maybe it is bad for you for other reasons. The idea behind this one is that mineral oil is a mild laxative. By speeding up the movement in the intestines, maybe what we're doing here is interfering with the absorption of statins. Therefore, what is being seen in reduce it is not a reduction in risk, is that by giving people mineral oil in the placebo group, you increase the risk in the placebo group. The reason I find this unconvincing is there's a couple of reasons. The first one is that if that were the case, then reduce it would have performed much better than you expected, given its dosage. So I built a linear model for each one of the variables that we analyzed, for which we had data, without using reduce it and without using strength. And I used it to predict what the risk reduction should have been in strength. If the bad placebo hypothesis were right, then I would have expected to see a much, much larger reduction, particularly for myocardial infarction, which is the one outcome for which we have very strong evidence that the effect is dose dependent. But we didn't see that. Actually, we've just seen that for the most part, reduce it perform roughly how you expected it to perform. So it's not wildly more successful than you expected due to the dosage. The second reason is that, remember, if you take a look at the results of the meta-analysis, there's considerable evidence that EPA and DHA are cardioprotective. And that does not depend on reduce it. And this is research that has been conducted, yes, in studies that use more EPA than DHA, but the majority of this research is done using EPA and DHA together. So, the idea that reduce it got it wrong and the totality of the evidence which coincides with the results of reduce it still works. I mean, it's a little, it's contradictory. It's difficult to believe. This is the reason why I think the placebo hypothesis is wrong. It is entirely possible that that some effect having to do with the placebo may have increased a little bit the results of reduce it, but they do not explain the totality of the effect found in the trial. The opposing hypothesis is the only EPA works. Basically, it's only trials that only use EPA work and nothing else works at all. And this is not actually consistent with the totality of the evidence. That is the explanation that says that reduce it got it right. Strength, of course, got it wrong because they included DHA. It's not consistent with the totality of the evidence. If you take a look at the epidemiological evidence, which we already have, status, the amount of EPA and DHA in your body, predicts your mortality, particularly cardiovascular mortality. And this is research conducted in people eating fish and taking supplements, both of which contain a significant amount of DHA. So only EPA works, and that does not coincide with the observational trials that we have seen. It does not coincide with the fact that we know that if you put together all of the trials, then you find a significant effect, and these are interventional trials. And remember that the results of this meta-analysis are not dependent on whether you include reduce it or not. And this is evidence that was mostly conducted in using treatments that contain both EPA and DHA. Most of it contained DHA. More EPA than DHA, yes, but it contained DHA. And finally, remember that we did address this question. We did ask a question. We did build models to try to find whether there were differences between trials that use only EPA and trials that use both. And we could not find any difference. So the hypothesis that strength failed because it used DHA while only EPA works, that is not consistent with the evidence, both from interventional and from observational trials. And this brings us to the end of my presentation. And thank you very much for your attention. And if you have any questions, please let me know.
Aldo, thank you for a really comprehensive and careful analysis of the data. Really enjoyed it. I do see, I think heterogeneity of data is definitely out there, and your careful analysis really helps define, potentially why we see some of that. So I really appreciated that. And it's time for questions. I think we have two from the audience. The first question, EPA and DHA are mostly seafood derived. Do you recommend other sources for omega-3 fats?
EPA and DHA indeed mostly comes from seafood and actually algae. Algae is what produces EPA and DHA, and the EPA and DHA that you get in seafood, and it comes from consumption of the algae. There's some, okay, so there's a third fatty acid, ALA, which comes from vegetable sources, chia, linseed, things like that. There's very mostly newer evidence that links ALA to a reduction of cardiovascular risk. There's some discussion about whether this comes from converting the ALA to EPA and DHA, and in a majority of people, that conversion is inefficient. So it's difficult to tell whether the purely vegetarian sources are equally effective or not. There's not quite enough research behind that. There's some evidence that there's some cardiovascular protection, but there's very little research and only very recent. So I cannot really recommend that. I'm not saying that it's bad, but for you, it's just not enough to support the solid conclusion. Other than that, EPA and DHA is going to come from marine sources, with the exception that lately we're seeing some genetically modified seeds that produce EPA and DHA, and but they're not used for human consumption yet. So I think that at the moment it is just seafood that we will have to use for the source.
I guess I can think of like omega-3 eggs, maybe also. There's some less concentrated sources, and then supplemented, where they're actually putting EPA and DHA into dairy products and things like that. So obviously not as many omega-3s as a piece of salmon.
I have forgotten about the eggs. Thank you.
Yeah.
So we people are very bad at converting ALA into EPA and DHA, but chickens are very good at it. So if you feed chickens all of these vegetarian sources, they convert it and put it in the egg. The thing though is that the amount of EPA and DHA in an egg is about 50 milligrams or so. So if you're aiming to the levels of even the most conservative recommendation, which is 250 milligrams, that's 5 eggs a day, which is not necessarily the greatest idea. So as an alternative supplementary source, yes. And then of course, fortified products contain algal oil that are not seafood.
Right. Okay, and the other question from the audience, was pure EPA given as triglyceride or as a free fatty acid? So maybe this was directed towards the Reduce It study.
Reduce It. Every single study conducted to date has been done on triglycerides, the natural form in which this come, or as an ethyl ester. That includes Reduce It. Reduce It uses Placebo, which is an ethyl ester of EPA. The only study to date that has been conducted on a free fatty acid is Strength. Well, at least the only study that has been conducted to take a look directly at hard outcomes like this, and so that is a source of complication. It makes it very difficult to put strength into context because we don't know whether the chemical form, which is so unusual, had anything to do with the null results.
Yeah, I think one of the touts of free fatty acids is that they're absorbed fairly well, but it's a form that's not been studied in great number of studies. And I had so measuring blood is one way of determining compliance or looking for EPA and DHA in the blood. Did Strength and OMEMI, did they measure blood levels also in their two trials?
I don't remember whether OMEMI measured it or not. Strength did. So the thing is that, okay, now it gets very entertaining. Strength used a carboxylic acid, which actually increased the risk of gastrointestinal side effects.
Okay.
So because of that, a new coating was developed to make sure that the agent was not going to be released too early. And it's a new coating. So there's a question about whether the coating opened too late and that affected the absorption. Carboxylic acids absorb very efficiently, but they say new coating, and there's a question of compliance because of gastrointestinal distress. So all of these things actually have something to do with how much was absorbed and how much made it into the subjects. What we know, because blood levels were measured, is that there was efficient absorption. I don't have complete computations in here, but based on what I have seen, it looks like the absorption was less than what you expected for the dosage, but it was close to what you expected to see. So there was sufficient absorption. There was enough fatty acid going in there. The triglycerides were reduced. There was all kinds of evidence that there was quite a bit of absorption, maybe not quite as much as you expected, but way sufficient to find an effect. So absorption doesn't explain, absorption compliance do not explain that. So
Okay.
no, something else is going on. I suspect it's very interesting biochemistry there.
Yeah, it's compliance is always a number of clinical trials I've been involved with. It's always been an issue, I guess, for a number of patients. But I guess this sheer sample size of that study too negates it. But and then one last question: Dieberg and Bang's papers demonstrated the Greenland Inuits were consuming about 16,000 milligrams a day. I think the highest I saw in your data was about 6 grams of intake in your model that showed reduction of risk. Did you model beyond 6 grams at all? Or I suppose it's difficult to find cohorts with that.
I can't.
I
can't. I mean, yeah, the study with the highest dosage I found was 5.5 grams per day, but it was a very, very small study. So, I mean, I cannot go that far.
Sure.
You see that the evidence that we are seeing starts at about 250 milligrams. I forget the study that did that, and it ends with reducing with about 4 grams. Generalizing outside of that, and we just don't have enough data to do it.
Let me check one more time. Oh, there's one more question. What is the effect of statins in the strength study? At least I assume that statins were used based on the name of the study.
Yes. Everybody in strength was in statins, yes. And reduce it too, by the way.
Both of them. Pretty much standard of care.
Yeah, right. Most of them are studies of what additional protection may come from Omega-3 on people who are at a high risk and are taking statins, of course. But everybody's taking statins these days, so you cannot conduct a study without statins anymore.
Right. Well, that's all I have for you, Aldo. Thank you so much for a really awesome presentation and for being part of our AOCS meeting. Really nice to have you and to be working with GOED. So.
Thank you for the kind words. And everybody, of course, I mean, you have my contact information in the screen. If you have any questions, please let me know.